Hello and welcome to this presentation on animation. We'll look at several different types of animation. Most of the time you probably think of animating 3D characters with an underlying skeleton, but we can actually consider animation in a more broad sense where it's just something animating, something with motion. In particular, today we'll look at the camera, animating or moving the camera, 2D animations and 3D animations. And there can be other types as well. For camera movement or animation, what you may end up doing is creating a path with a series of positions and poses. Not very different from what they refer to as waypoint navigation in some AI steering behaviors. Basically, we have a camera here and we set up a series of positions along a path, and we interpolate the camera in those positions over time. And the interpolation is very similar to the blending equation that we saw with the 1 minus alpha, but in this case we're using 1 minus time. So if time ranges from 0 to 1 or is scaled from 0 to 1, then we take the current position and scale it by 1 minus t, and we take the new position and scale it by t. So if t is 0, we get the position. If t is 1, we get the new position, and if t were 0.5, we would get something halfway between the two. And so this way we can interpolate between different positions for the camera. In many of the math libraries, you'll actually see a function to assist in doing this. They refer to it as LERP, for linear interpolation. And in addition to setting up a path that has positions of the camera, we could also add to that an orientation, either with a rotation or something we'll see later called a quaternion, or a series of look at points and up directions that we can interpolate between. So this is relatively easy to implement if you just create a vector of points. Then you could create a path for the camera through your scene and interpolate the position of the camera. And parallel to that, in addition to the vector of points that you have, you could also create a vector of look at positions as the camera is moving and interpolate between those look at positions. You create a nice camera movement through your scene. With 2D animation, one common technique that we'll look at today is what they refer to as sprite sheet animation. In this image here you see some type of cat running, and it's a sprite sheet made up of a variety of different cells. And in this case the sprite sheet has 4 rows and 2 columns of cells for a total of 8 different images. And the idea is that you could use this as a texture map and create texture coordinates that outline the first cell, and actually create a list or a vector of texture coordinates for each of the cells, and then as time goes by swap the texture coordinate from the first cell to the second to the third to the fourth, and so on. And so this is one example of doing 2D animation with a sprite sheet. Of course, you can loop this animation with the modulus operator. Once the index reaches the last cell, as you increment it and do a modulus by the total number of cells, it should loop back to the first one. So let's take a look at an example of this. In the code for the poly object, I've added this couple of functions here, one called create sprite sheet, create sheet animation billboard, and an update for delta time, and an update vertex buffer. So the idea behind update vertex buffer is that if we change the texture coordinates in the vertex data, we've got to send that to the GPU. And so that's what this does here. We create this map resource, which is our vertex buffer, and we copy the vertex data into this resource pointer object, and then once that's done, we unmap it. So it's a pretty simple step, but it's important to remember to do anytime you change the vertex data if you want to see those changes reflected in the output. In this case, we'll be changing the texture coordinates for the vertices mapping into different cells of our sprite sheet. When we create the billboard this way, we pass in the number of cells and the number of columns and rows in the cell. And this should probably be reversed. I don't know. I guess it's okay. Number of columns would be across. That would be the x direction. Number of rows would be the y direction. So that's fine. We create a regular billboard, just like we did before, with 4 vertices. Although there's one minor change in that the previous version of Create Billboard actually made duplicate vertices. So a billboard only needs 4 vertices, and we can use the index buffer to create a triangle 0, 1, 2, and then create another triangle 0, 2, 3 with just a total of 4 vertices. The previous version of this billboard actually created 2 complete triangles, each with their own vertices, for a total of 6 vertices, so we had some duplicate vertices. Here we can be a little more efficient and just add the vertices and then add triangles with indices. So it's real similar, but a little bit different in that we're now using shared vertices. It makes the swapping of the texture coordinates a little bit simpler. Here's where we compute the texture coordinates for the billboard for each cell. So we know that the sprite sheet, the entire texture range on the sprite sheet is from 0 to 1, starting in the upper left-hand corner. So if we take 1 and divide it by the number of columns, we'll get the size in texture coordinate of each cell across and the height of each cell in texture coordinate. Then we can just do a loop for each row, for each column, create a texture coordinate, and I prefix this with BL, meaning bottom left. So what I'm doing is computing the bottom left texture coordinate, or the texture coordinate at vertex 0. And since the vertical texture coordinate, the y value of the texture coordinate, is positive going down, we have to add column plus 1 when we multiply by the cell size and texture coordinate in the vertical direction. And then I just push this into this animated texture coordinate list, which is simply a vector of vector 2. So I'm using the simple math vector 2 that we got from the DirectX TK. There's a lot of really good math functions in there, and we'll see more of them later on in this presentation. So we're using the vector 2, which has an XY coordinate, and the standard template library vector, which is just a dynamic array of whatever type we put in this template. The cell size, that's also being calculated, so it's 1 over the number of columns, the number of cell columns, the number of cell rows. That's the cell size. And then the current cell is the index or the frame number that we're at. So in my particular sprite sheet, I've got a fire here, and I've got 6 by 6 cells. Some sprite sheets that you may find online, the cells are not evenly distributed. They're packed in as tight as they can, and the problem with that is you don't know where the rectangles start and stop, so you would need a separate data file for those where the rectangles start and stop. So you can use them, but you're going to have to go through and map out what each X and Y should be in terms of your texture coordinates, and that can be rather time consuming. So my recommendation, if you want to use your own sprite sheet to do a 2D animation, get one that has the cells evenly distributed, regularly distributed throughout the sprite sheet. So in this case, it's 6 by 6, and so it's easy to say that, okay, well, the texture coordinate here on the left side is going to be 0, over here on the right side is going to be 1 divided by 6. And then for the second cell, it's going to be 1 divided by 6, and over here on the right side, it's going to be 2 divided by 6. So this is the layout of the particular sprite sheet that I'm using. So these loops create the texture coordinates for each cell in the sprite sheet and push them into this list. So then now here I just set the first one. So the current cell is set to 0, and I just set the texture coordinate for vertex 0 to 3 to the current cell, so that's the bottom left. And then notice in this diagram, 1 is up in Y, which is actually negative in texture coordinate space. So remember, the Y texture coordinate is positive down, so we end up with offsetting this bottom left by 0 and minus cell size Y. 2, we offset the bottom left by cell size X minus cell size Y. And then the third one, we offset the bottom left by cell size X and 0. So we're just going across in the X direction here. So that sets up the texture coordinates for the first cell. When we get an update, I'm creating a local time variable to keep track of the time that's elapsed. And I'm asking the question, if the time gets greater than 0.25, which is 250 milliseconds, a quarter of a second, then I'm updating the current cell. So I say the current cell equals the current cell plus 1, and then mod it by the number of cells that I have, which is the number of texture coordinates in this texture coordinate list. So this way it'll loop back around once the current cell, if the current cell were 35, add 1, we get 36, 36 mod by 36 gives me a 0, so it loops back around to 0. And again, I set the texture coordinates, reset the time back to 0, so that we'll start counting up to 20.25 seconds again, and update the vertex buffer, which copies those new texture coordinates into our DirectX vertex buffer. If I'm not updating the cell, then I just increment the time. So this is only going to update 4 times a second, which may not be fast enough, but we'll take a look and see how that works. In our application, then, one of these billboards is going to be an animated billboard. and it turns out it's billboard 1. I call create animated billboard and pass in the 6x6, so that's the number of rows and columns, cells. I'm translating the billboard. The billboard starts at 0, 0 and goes to 1, 1. So I'm transforming it to be centered at the origin and then moving it back in Z and then scaling it in the X and Y directions to make it larger and then translating it again to put it where I want to. So I've got a series of transformations to make it the right size and then move it where I want to. Create the DirectX objects, load up the texture. We're not going to use alpha. Well, we are going to use alpha, but not out of the... I don't believe there's any alpha in the texture. We have an equation. I've modified the equation in the shader for the alpha. The update then, every time we get an update, we're just going to call billboard 1 update, pass in the delta time and the device context so that we can update the vertex buffer. The render also looks very similar. We get the composite transform, the view and the projection matrix, set the shader data, and update the constant data, set the constant buffer, and render. Notice in the render we're setting the texture here for the pixel shader as well. So in the shader, the one big change that we have, most of this is the same. You're familiar with this constant buffer that we used, the vertex in type, the vertex out type. The vertex shader just converts from local coordinates to the homogeneous screen coordinates. The texture data is just passed through, so this is very similar to the texture demo that we've seen previously. The pixel shader samples the texture, and then here we do a modified version of color key transparency. So since my sprite sheet has very dark color around the flame, I use that fact for, I take advantage of that for the transparency. So I compute the length of the texture color. So instead of XYZ, it's really RGB data, and I get the vector length of it. So if the color is very dark, then that means the length will be very small. And if that length is small enough, then I use it to set an alpha value, which means it's going to be really transparent. A small value of alpha will be almost completely transparent, so that hopefully we just see the flame and maybe some of the smoke around the flame and not the rest of it. Better ways to do this, but this is the sprite sheet that I have found to use. So let's take a look and see what we get here. In the output, you see we've got the pyramid and the sky texture in the background, and you see I've positioned the texture, the animated flame texture, right at the top of the pyramid. And we can zoom in on a little bit. And in wireframe, you know, it's just you can hardly see it because of the transparency, but it's just 2 polygons here. And you can see it's animating kind of slowly. Well, it's only animating 4 times every second. Maybe we want to increase that. If we go to our update, we can reduce this amount of time and say let's do this 10 times every second. And you can see it's animating faster. So this is one example of animating, 2D animating with a sprite sheet. And notice this is not actually a billboard. I don't believe this is going to face the camera, so as I move around, yeah, you'll see how it's flat, right? So in this case, I don't have it hooked up to the billboard code that always faces the camera. This is just a flat polygon out there in space. We'd have to modify that. Let's move on to 3D animation. With 3D animation, there's a variety of different ways of doing it. One is that you can just keep track of the position of all your objects and the position of all your vertices. So you could have, if your object has, say in the case of a cube, if your object has 8 vertices, you can animate the cube by having 8 lists of vertices. So as you step through in time, you would go to the next set of 8 and the next set of 8 and the next set of 8 and interpolate between them. Obviously this can get quite data intensive. You can have lots of data needed for this type of animation. Another more commonly used technique today is storing the pose or the rotation or the orientation of a connected hierarchy of segments or arms or bones, as you've seen in some skeletal animation. So in this case, an image over here, we've got a robot arm, and it has maybe 1 arm, 2 arms, 3 arms, and each one has different degrees of freedom, meaning different amounts or directions that it can move. And if we know the position of the base and we know its orientation and length, then we can take that base, scale the length by the particular orientation or displacement vector, and we can get the position of this. And then if we know the position of this bone and we know its orientation and length, we can get the position of the next one, and so on and so on. So all you need is a list of lengths and a list of orientations or poses for each arm or segment in the hierarchy. And the orientation, if we want to interpolate from one orientation to another, it's really just a rotation about some axis at the base of the segment. And we can store that rotation in a matrix, but it turns out that matrices do not interpolate very well. Rotations stored in matrices do not interpolate well. So instead, we use this thing called a quaternion. I'm not sure if you've seen this in math courses yet, but a quaternion is a 4-dimensional vector that can be used to represent a rotation. So a quaternion has an XYZ W, and you can take a rotation around a particular axis and compute those XYZ W values. I won't go into details on the math here, but there are some nice functions in the Simple Math library, and one additional one that I'll share with you today that you can use to create quaternions to represent certain rotations. In particular, one function that I like is being able to compute a quaternion given a from and a to orientation. So if you have a direction pointing, say, down the x-axis, and that's your from orientation, and then you have another vector that's pointing up in the y-axis, and that's your to orientation. Well, we can see that the rotation from the x-axis to the y-axis would be a 90-degree rotation about the z-axis. In general, it's not as intuitive how to get that rotation or to get that transformation, that rotation from a given orientation to another different orientation. Well, here's a function that does this basically we first check to see if the two orientations are the same. So the code here doesn't work if the two orientations are the same, because the cross product of two parallel vectors is not well defined. It doesn't work very well. So we compute the dot product, and again, this is using the vector math, both vector 3 and quaternion, from the simple math library out of the DirectX toolkit. Compute the dot product, and if the absolute value of the dot product is really small, then we just return an identity rotation. So quaternion identity is similar to an identity matrix, but this is an identity quaternion, so it represents 0 rotation. If the dot product is not really small, meaning that the from and the two vectors are not parallel, then we compute the cross product, and the formula for the quaternion that we need is the XYZ components of the cross product, and then the W component is the square root of the from vector squared and the two vectors squared multiplied by each other, and then we add to that dot product. So that's a formula that you can look up to compute a quaternion given an original orientation and a destination orientation. Well, I call them a from orientation and a to orientation. This quaternion needs to be normalized, and then we return that result. So that's it's going to be useful in our 3D animation, as we'll see. So again, the idea behind our 3D animation is we're going to create a hierarchy of connected segments, and each segment has a length, and each segment has an orientation represented by a vector, a direction vector. In this case, the orientation of this one might be straight up in the y direction. In this case, it might be negative x and negative z a little bit. In this case, negative x, negative z, and negative y a little bit as well. So once we have those orientations as direction vectors and lengths, if we know the base position, we can compute the position of the next segment, and the next segment, and the next segment, and so on. One question remains. Is what should the orientation of all these segments or bones be? So for example, if I want the arm or the character or whatever to touch a certain point in space, what should the orientation of all these segments be? And this is the subject of a lot of research and a lot of math. How do you compute the poses and positions of the different arms? So the problem is, given a desired location, how do you compute the position and poses for each of the segment? And there's a few different solutions. One is that we could create, you could have an artist or yourself create, using a modeling package like Blender 3ds Max, you can create a series of keyframe data. So you don't have to calculate the position and orientation of each segment. It's stored in a file, an animation file. And then you can just go through there and interpolate between each one. You could also use motion capture to capture some real motion and use that data. It turns out there is what they call an analytical solution, or a set of equations, but it's limited. It doesn't solve the general case where you might have a lot of different arms that have a lot of degrees of freedom. It's limited to 2 arms, or maybe a little bit more if there are constraints such as limited movements or limited degrees of freedom. The more general case, where you may have more than 2 arms and more complex degrees of freedom, there are solutions that will approximate. You can iterate and approximate a solution. And there's one that's very math intensive, referred to as Jacobian inverse, and there's one that's fairly recently developed, referred to as Fabrique. and that stands for forward and backward reaching inverse kinematics. And that's the technique I'm going to show you today. It's surprisingly simple. It involves some iteration, but since we're animating over every frame, it tends to work out really well for us. So let's take a look at this Fabrique algorithm. This is a diagram showing a set of connected arms. So there's L1 was the first arm, and L2 is the second, and L3 is the third segment or arm. And we have a starting location, and we have a goal or a desired location. The light blue is the current orientation, and the violet or pink is the orientation after the first iteration of the Fabrique algorithm. So Fabrique is forward and backward reverse inverse kinematics, and we actually start with the backward iteration. So there's a backward loop and there's a forward loop, and actually when you start Fabrique you start out with a backward loop. So what happens is in the backward loop we start at the end, not at the beginning. We're going backwards, and we take the end and we put it at the goal, and then we compute a direction vector from this modified P3 value to the original P2 value. We normalize that and then scale it by the length, and that gets us this new P2 value. So we take the original P2 and subtract the modified P3, normalize it, scale it by the length of that third segment, and that gets us to this point. We do the same thing going to P1, we do the same thing going to P0, and that's the end of the reverse iteration for the Fabrique algorithm. So notice it has the end at the goal, but now the beginning is not where it should be at its start position. So it's almost like the arm has been dislocated, right? Well, we're going to fix that with the forward iteration, and so the forward iteration moves P0 to the origin, creates a vector from P0 to P1, scales it by the length of P1, and then we get a new position. We repeat that to P2, we repeat that to P3, and we won't be exactly at the goal, but we'll be pretty close. And if you do this iteration a few times, most of the time you'll be really close to your goal. And in fact, because we'll be placing this code within an animation that's going to run every frame, we can actually get away with doing very few iterations of these backward and forward Fabrique algorithms. So let's take a look at the code needed for this. I have added a new module called Fabrique arm.h, and as we've seen, it has this math function for computing a quaternion. The Fabrique segment is an arm segment, and it's going to be inherited from a poly object, and in particular we are going to use the cylinder that we saw earlier this session to represent an arm of our skeleton or robot or whatever. Each Fabrique segment has a length and a radius would default to 1. And each Fabrique segment is going to have a scale. So how do we scale it? How do we rotate it? And how do we translate it? So each cylinder will have its own scale, rotation, and position. We also need to animate the arms. We need to know the current position and the desired position, and the current look at point and the desired look at point. And this will help us to animate the arms or the segments of our little animated robot arm or whatever. So we set these all up in the constructor, and we add a transform for the scaling, for the rotation, and for the translation. And so it's important to remember when we add the transform, these are the order in which these are going in. So this is going to be, the scaling is going to be at 0, the rotation is going to be at index 1, and the translation is going to be at index 2. The current position, desired position, we set to 0. So recall that our cylinder is initially placed at the origin, and it's looking down the x-axis. So we set up the current look at to be looking down the x-axis. So unit x is 100. When we do the animation, passing in delta time, and delta time should range from 0 to 1, we're going to interpolate, linear interpolate between the current position and the desired position. And it may be the same, it may be that we never move it. And we're going to interpolate between the current look at and the desired look at. And we can compute a displacement vector, which is the desired orientation. So what we're looking at in our current position, that's the orientation that we want. And looks like we have a mistake here. Actually, our cylinder is created positive down the z-axis. So once we get the displacement between our current look at and our current position, we know that the rotation that we want is the quaternion that gets us from the z-axis to that displacement. Once we have that, then we can set that rotation as transformation at index 1 and the position that we computed as the translation. That'll be the transformation at index 2. The Fabrique arm, the entire arm, has a base position, the current target, and the desired target. And so the desired target is what's set by the user. That's the position that we want to. The current target will get animated over time to move from the current thing that we're touching to the new desired target that we want to reach out to. The arm itself is a vector, standard template vector of Fabrique segments, maintaining a list of points and a look at. I'm not sure if all these are used. Some of these variables may not all these variables may be used. Let's look at the Fabrique algorithm. Here's the reverse that we saw. For the reverse Fabrique algorithm, we get the number of points, so that's P0, P1, P2, P3. And we start at the end and set that equal to the target. And then we start moving backwards down to 0. We get a direction vector going backwards, normalize that, and scale it by the length of each segment to get us the next point going backwards. The forward is very similar. We loop through the number of points starting at the start position, get a direction vector moving forward, scale it by the length of each arm, and that's the new point. There's some functions here to return the error and the error squared. So the error is how far away is the end point from the goal or the desired point. The solve is what we use to solve for the orientations, and in this case I'm only doing one iteration of the reverse and the forward Fabric algorithms. You can do more than one iteration, but it turns out because we're animating this and doing an additional iteration every frame, it turns out that this works well enough. So here's the update. We update the target, animate the target, solve for that target, and then set the positions of the arms, and then animate those arms toward that target. The end position is just the back of the point list. Setting the target, something that we can call. Animating the target just uses the lerp function from the current target to the desired target over time. And animating the arms, given a time, we go through each segment and animate it. So in our code, what we've got, when we go to use the Fabric module, we have to include Fabric.h, and then we create an object of type Fabric arm. Here we initialize it and we pass in some arm lengths. So let's create it with, say, 1 and 100. So what this means is that right now our segment is going to have just a single arm, and it's going to be 100 units long. Its position is going to be at the origin, and we pass in those arm lengths to construct it. We set a texture, create the DirectX objects, and then we'll modify the position of the camera here. I think that'll work a little better. In the update function, all we have to do is call the Fabric arm update, pass in the time, and then in the render, I actually have a list of spheres that I am rendering. So here's the list of spheres that I've created. I think there's 4 of them. And then here's the loop that goes through each segment of the Fabric arm. Because each one is a cylinder, we get its transformation, set it, and render it. What are we doing with the sphere list? So the sphere list gives us a list of poly objects, and what I'm going to do is allow the user to select one of the spheres in the sphere list. In order to do that, I'm going to use the picking capability that we discussed last time, and for that I need the position of each sphere and the radius of each sphere. So when I do the initialization, I'm creating a sphere radius of 42. It'll be the same for all spheres. You could have a separate sphere radius list, so each one could have a different radius if you wanted. I've resized the sphere list and the sphere position list to be 4. So then here's the position of each of the spheres, and here's the code that creates each of those spheres with different texture maps and the different sphere positions. Notice that the radiuses are all the same. Now here's where we render all those spheres. So if this builds and runs okay, So I'm not seeing anything on the output. I'm not sure exactly why yet. I'm thinking that it has something to do with the camera. Not being set up, the camera in the scene, not looking at the objects or something. Let me see. So the camera position is back a ways. I'm still not seeing anything on the output.